So what is the common collector configuration or common collector amplifier does? Yes, common emitter amplifier is something. What is common collector? Yes, current amplification. Do you people do the amplification there? What is the gain of the common collector amplifier?
Buffer.
What is the gain? I'm asking what is the gain?
1. What is it?
It is basically 1, and it is 1. Similarly, this common drain amplifier that we're going to see, okay, so it also a kind of unity gain, but not exactly unity gain. Practically we won't get unity gain, okay, so we may get somewhere 0.8 or 0.8 for 0.9 times the input, okay. So most of the times we call this as something like a source follower also, okay. So this common drain amplifier is sometimes called as source follower. Okay, so we'll try to see what exactly this is all about. Okay, so going ahead with the common drain amplifier. Yeah, so this is M1. Okay, the transistor, NMOS transistor, what we are taking. Yes, and now this is VDD. Okay, drain we are connecting to the VDD. This is V in, and this is the source. Across source we are taking the output. You can see that drain is acting as a common between the input and the output. Okay, so gate is that the input, source is at the Vout, and we have something like a source resistance that is connected to ground. Okay, so this is your common drain amplifier. And as you know, since the passive component occupies more space in an IC, and it is not common practice that we do, and also there is a lot of dissipation in terms of heat. Okay, we replace this passive device with an active device. Okay, so this just have something like this. Okay, this is M1, the drain, the source, VDD. This is where the V in we apply across source, and we are taking the output, and then we use one more transistor, NMOS, and in this case this NMOS is acting as a load. Okay, this is the load resistance or the source resistance side, which you call typically a load, right? Because there will be some drop. So again we are ensuring that this particular M2 transistor will be driven in terms of saturation. Okay, so it will be operating in the saturation, so we will provide some base voltage, okay, or biasing voltage, not the base, it is the biasing voltage. Biasing voltage we provide, ensuring that M2 operates in saturation. Okay, and since the common drain amplifier, it is a kind of the gain AV is up ideally. Okay, so ideally it is equal to 1. Approximately we may say 0.8 to 0.9 times the V. That is what the gain is all about. Okay, so to ensure that, we make sure this M1 will also act or operate in terms of saturation. Okay, this is what, in other words, we ensure that the drain to source of M1 transistor will be equal to the gate to source of this minus VTN. Similarly, the drain to source voltage of M2 transistor will be minimum equal to VGS2 minus VTN. Okay, so this is the condition for the transistor to be in saturation. Okay, so that's why we are ensuring that this is the one. Okay, and this gain of common drain amplifier, as you have studied earlier, so it is basically given by GM divided by 1 plus GM plus GMB, and this GMB is basically the body transconductance into R0 into R0. So this is what the gain is all about. Okay, I'm not going to derive this. Okay, so the gain of this common drain amplifier is given by transconductance times the R0 divided by 1 plus GM plus GMB whole into R0. Okay, So for most of the cases, this GM plus GMB into R naught is very much greater than 1. So it is left with GM R naught, and also this GMB is very much less compared to GM. So we will going to neglect that. It is a GM R naught. Okay, AB. If you are not letting the GMDB to be very less, it will be GM plus GMB into R naught. Okay, or approximately I can say it is GM R naught by GM R naught. So it is equal to 1. So that's what the gain of this common drain amplifier is, basically 1. Okay. So there are 3 aspects that we have to now calculate. One is what is the W by L ratio of this M1, that is this M1. Okay. Second thing, what is the W by L ratio of M2? What is the biasing voltage? Okay. And what is this DC biasing voltage? Okay, that we have to find out. And in order to find out this, and the moment when these two are in saturation, I can say that whatever the current that is flowing in ID1 is the same current that is flowing in ID2. Okay, so this is what we consider. Okay, hope till this point is okay. What is common drain amplifier? The drain is common between the gate and the source, where for the gate we are applying the input, at the source we are taking the output, where source is connected to the source ground through RS, and RS is replaced by the equivalent active load by using one more NMOS, and the gain typically is approximately 1. Practically, when I say take, it will be in terms of 0.8 to 0.9. Okay, so going further, okay, so now we have to find out all these things, right? The WL ratios, the biasing voltage, the VIN and all. Okay. So we know the drain current, right? Drain current is basically, and make sure that both of your transistor, the M1 as well as M2, they are operating in the saturation region. Okay, saturation region, and the current corresponds to the saturation current. Okay, it is given by 1 by 2 mu n Cox W by L of 1 into VGS minus VTH square. Okay, so this is the drain current under saturation. Why we are considering the saturation? Because both the transistors are operating in the saturation region. Okay, so only ensuring that we want the gain to be basically a 1, right? Okay, so this is 1. And with respect to transistor M1, I can A can be written as IDS1, that is the drain to source current of 1, is half times mu n Cox W by L of 1 into VGS minus VTH square. This is 1, I say. Okay, VGS1. And what is basically a VGS1 is all about? This is VG, this is S, this is the gate to source voltage of M1 transistor. Okay, I just write it here also for your understanding. So we have VDD, this is drain, this is M1, this is source, this is gate. This is what I mean by the gate to source of 1. Okay, this is V out and this is my V in. Yes, and VGS is basically what? V gate minus V source. Okay, this I can write it as half times mu n Cox W by L of 1 into V in minus Vs minus VTH square. Okay, this is what I'm just replacing VGS1 by V in minus Vs, and that is given by half times mu n Cox W by L of 1. V in is basically DC voltage, and we'll whenever we are applying the V in DC, it will be from 0 to maximum, and maximum we'll consider the VDD itself. Okay, so V in, since we apply minimum to maximum voltage that we are assuming, we can treat this as something like VDD minus Vs minus VTH square. And what is Vs? Basically, it is V out, right? So we are replacing Vs as V out. Okay. So this is basically our V out. And why V in we are changing to VDD? Because V in is the DC, the biasing voltage maximum we are applying is 5, and that's what we are replacing V in by VDD. And Vs is basically the V out, and hence our source to drain current of M1 transistor is half times mu and Cox W by L into VDD minus V out minus VTS square. Okay. So in this case, we know that VDS is 5. So VTH will take it as 0.7. Okay. And now W by L of this ratio we'll keep it as 1 for NMOS. Okay. And we'll consider IDS 1 to be somewhere as 0.5 milliamperes. Okay. Okay. So this is what. So let IDS 1 is 0.7, VDD is 5, VT threshold is 0.7, W by L ratio, let the lead and wind ratio is 1. It may be 6 by 6 or 5 by 5, whatever you want, you can take. It is 1. So we know VDD. Okay. So we have to calculate what is our V out. Okay. So in order to calculate V out, we have other variables. That is, we don't know what is our mu n. We don't know what is the Cox. The moment we'll come to know what is mu n and Cox, we can calculate what is the V out there and how to get this mu n and Cox. Okay. And this mu n and Cox we know that basically it is epsilon naught epsilon r divided by Tox. And if it is a silicon means epsilon r would be 3.9. And epsilon naught, we know that it is 8.854 into 10 to the power of minus 12 farad per meter. Yes. So we should know Tox in order to get Cox, and we should know the mobility of this. And this mobility, the oxide, all depends upon the technology. Yes. If the technology differs, the mobility also differs. Okay. So I mean, especially the oxides and all. Okay. So in order to know what is the mu n and mu ox, all of you know that C5 models, right? Yes. When you're doing the simulation, you have included C5 underscore models dot text. Yes or no? Fast.
Yes, sir.
Yeah. So that's what. Now, if I just open that C5 models, okay, you can just open in your thing. Okay. So this is what BSIM models for C5 process. Okay. And here, if I just see this model NMOS, okay, so you can see what all the parameters are there inside this. Okay. Version is that. Can you see this oxide thickness, Tox? Yes? Yes or no? Fast. Yes or no?
Yes, sir.
Yes. And how much is that? It is 1.39 into 10 to the power of minus 8 meters. Oxide thickness, right? In terms of meters. Okay. This is what. Okay, I've written here. So I'm ensuring that my oxide thickness is taken here. The moment I have the oxide thickness, and if the oxide is basically silicon dioxide SiO2, then I can calculate Cox because I know the Tox. Epsilon naught is the relative permittivity. So I can get Cox calculation, and it is somewhere around 2.484 into 10 to the power of minus 3 farad. This is the Cox. Okay. So how to get the Cox? We should know what is the material, oxide material, in order to get the epsilon r. Yes. And we should know what is the oxide thickness, and this oxide thickness we can get from the C5 models. Okay, and this is where the C5 model all about, and this is for NMOS. We are dealing with NMOS. Oxide thickness of NMOS is this. And similarly, I want the mobility. Okay, each technology will define all these parameters. Okay, so I have mu naught. Yeah, So this is the mobility. Yes. So mobility mu n. Okay, I'll write it here. Mu n is given by 0.045843 meter square. Okay, so this is the mobility. Yes. Now, known the mobility with respect to the technology file, and this technology file is basically 0.6 micrometer. Okay, 0.6 micrometer is the technology that we are dealing with. Okay, so we know the mobility. We came to know what is CMOS. We have assumed a W by L of NMOS. We have let the IDS, that is a drain to source of M1 transistor, to be 0.5 milliamperes. We know what is VDD, sorry, and what is VTH. Okay, so we can find out what is the V out from the expression, and going with the solution, solving that particular expression for V out, we get V out somewhere around 1.398, so which is approximately, we can assume as something like 1.4 volts. This is the V out. So by knowing the parameters of the mobility, the oxide, the W by L, the current, okay, we can find out what is the V out of the transistor. And now we have to find out the W by L ratio of the second transistor, that is IDS2, which is given by 1 by 2 times mu n Cox W by L of 2 into. Now when we go with the VGS, we have something like this, right? This is VDD, this is source, the drain, the source, the drain, this is V out, this is V in, this is VB. Yeah, so now VGS minus VTH, VGS is basically VB minus 0, because source is at ground potential, the source is at ground potential, V in is VB, so VGS is basically VB minus VTH square. Okay, previously the VGS was V in minus V out, but now it is VB minus VTH, and that is given by half times mu n Cox W by L of 2. Okay, and can I write it as something like VDS2 square? Yes or no? Fast. Can I write VB minus VTH whole square as VDS2 whole square? Yes or no? Fast. Fast. Yeah. Can anyone tell me how come VDS2 is equal to VB minus VTH? Since M2 is also operating in, M2 is also operating in saturation. Okay, M2 also operates in the saturation region. Yeah, so we know that for the saturation region, the VDS2 should be VGS2 minus VTH. And what is VGS2? It is the gate voltage is VB minus source voltage is at 0 minus VTH square. Yes, and this is nothing but what? VB minus VTH square, and VB minus VTH, sorry, this is just VGS minus VT, this square won't come, just, and instead of VB minus VTH, I'm just replacing this by VDS2. Okay, but what is VDS2 according to us? This is VDS2, right? VDS2. What is VDS2? It is nothing but what? V out. Okay, drain to source voltage is basically V out for us. So that's why this IDS2 will become now half times mu n Cox W by L of 2 into V out square. And since the V out for M1 and M2 are common, this V out we are replacing by 1.4 volts. IDS2 is equal to IDS1. That's why I'll just take 0.5 milliamperes. Yes. Mu n we have just took as something like 0.0458 meter square. COX we just calculated as 2.484 into 10 to the power of minus 3 farad. Okay. So I know V out. Yes. I know what is V out now. Yes. I know what is COX. I know what is mu n, and I know what is my IDS2. I can calculate W by L2. Okay, which is approximately we get in terms of somewhere around. If you if you just substitute all this mu n, okay, mu x, all those things, you get somewhere around W by L as 4.59 as. Okay. In this, I just let L to be 4. Okay. Approximately, I get W to be a 20. Okay. Just 4.59. I'm taking it as 5. So 5 4 is something 20. Okay. So we assume the W by L of 1 as 1. That is the M1. You can take W by L as 1 by 1, 2 by 2, whatever. And W by L of 2 as somewhere around 4.59, where let L4, we can calculate what is about W, that is 20. And we are calculating this W by L and the V out considering the drain to source current of M1 and M2 operating in the saturation. Okay, all this. So hope this design is okay. I'll just repeat these things. Yeah, this is the common drain amplifier. We are replacing the passive load with the active load and ensuring the active load is operating at in the saturation. And we are also ensuring that the saturation of M1 also is operating in the saturation region. Okay. And the gain predominantly is 1, not exactly 1, but ranging between 0.8 and 0.9. And now just since both the transistor are operating in the saturation region, yes, so we are writing the saturation current, and it is given as ID equals half times mu n COX W by L into VGS minus VTH. And writing for the individual transistor, it goes something like this. For M1, we have written something like this, and we are substituting VGS1 as V in minus VS, VS as V out, and V in as VDD. That is the maximum voltage that the V in can go along the biasing. Okay. And considering the VDD, VTH, W by L of this IDS, and taking the technology file information on the TOX and mu n, we can calculate what is called the V out, and V out we got somewhere around 1.398, that is 1.4 volts. Okay. So keeping this V out in mind, we are going to calculate what is the W by L of the load resistor in the M2 transistors. M2 transistor. IDS2 is equal to IDS1. Mu n is known. COX is already calculated. And VGS is basically VB minus 0, which is VB minus VTH whole square. And VB minus VTH is nothing but what? VDS. And what is drain to source voltage? It is basically a V out for us. So we know V out. We know what is mu n COX and IDS2. We can calculate what is our W by L of 2. That is 4.59. Assuming the L as 4, we can get the W to be 20. So this is how the common drain amplifier design goes with. Okay. Hope this is fine. You're taking the value of mu n and you're calculating COX based on the technology file that is there in the C5 models. Okay. Yes, no. Fast. Hope this is fine.
Yes, sir.
Yeah, so now I'll just we'll go along with the simulation using the electric tool. Okay, so you can see two NMOS, NMOS 1 and NMOS 2. Okay, I'll just zoom this. Okay, so this is NMOS 1 and NMOS 2. Okay. Yeah, so I'm just showing the properties of M1, that is the transistor which is now in the common drain configuration. I'm just taking width by 6 by 6. You can take anything because ratio remains same. You can even take 2 by 2 or 1 by 1 and check. Okay. This is one. And then accordingly, I consider the W by L of the one more load device as 20 by 4. Okay. The width is 20 and length is 4. And this is the biasing voltage and this is the V in voltage. This is NMOS and this is both are NMOS. This is the Vout, and we have a VSS which is grounded, and we have VDD which is the powered up. Okay, so this is the simple circuit we have. Yeah. And then this is the SPICE code for the DC analysis. Okay, so you know what thing to be included. I have VDD from VDD to ground with the DC of 5 volts, VSS to ground, DC of 0 volts, VB. Okay, this is very interesting now. VB, make sure that you have the biasing voltage for M2 in order to operate in saturation. Make sure that that is one of the important aspects. Okay, here. So your VB should be less than the Vout. Okay, and it should be less than 1.4 volts. Okay, you can consider VB to be anything less than 1.4. So for example, we are taking somewhere around 0.9. Okay, 0.9, 0.8, 1 volts. Okay, but make sure it is less than your Vout. We can't, because biasing voltage can't exceed your Vout. Okay, so that's why make sure that V bias is 0.9, and that is what we have mentioned here. Okay, the VB is this, and V in we are varying from V in 0 DC to 5, and the maximum is this. And we are doing the DC analysis. Okay, dot DC V in ranging from 0 to 5 in the steps of 0.01. Okay, so this is what we have. Okay, so we'll try to run this. Okay, so it's a LCD amplifier. Just a minute, I'll come back. Yeah, so let we have this trace here, V in and V out. Okay, and you can see that this green is V in, which is ranging from 0 to 5 volts, and you can see the blue one, which is V out. No doubt it is becoming linear. See, initially it is not. From 0 to 1 it is 0. Later it is starting to increase, and where exactly it is becoming linear, that is very important for us. Yeah, you can see that. Almost you can see that from 0, you can see that they are not parallel. Okay, after some voltage, so after you can see that 3.5 above 4, so from here onwards they are eventually becoming something called a parallel. Okay, and that is what the V in. Okay, so the Vin, okay, just right here. So this is very important now. The Vin biasing voltage is very important now. Okay, where exactly my V out follows the V in. Okay, so you can see that till some voltage it is not linear, right? So initially it is 0 and then it is start increasing, but after some voltage it is becoming exactly parallel. Yes or no? Fast. We have to find out the biasing voltage, that is the DC voltage for the M1 now, V in. Are you people getting what I mean by this? Yes. At what voltage onwards my V out, okay, exactly parallel with my V in. That means following. It is a kind of linear, right? So here it is 0 and then it keep on starting, but you can see it, they are not exactly parallel. Okay. So up to some point they are linear. I'll just go back to original. You can see that from up to one point it is 0, then it is increasing, and still you can see that they are not parallel exactly. And after 4 voltage onwards, you can see that there is some kind of parallelism that is coming. Okay, and now we can either consider voltage 4, 3.8, 4.2, all these things as something like a biasing voltage. Okay, so that is what the V in that we have to understand, okay, or get from this DC analysis. Okay, so from DC analysis, just go to the next one. So from DC analysis for common drain amplifier, okay, so when we plot V out versus V in, okay, we should see from which voltage onwards my V out is following V in, and that voltage is your biasing voltage for M1. Okay, and that's what we could see from this. I can't consider the biasing voltage to be 0.5 because output is not following input. I can't consider the 0.1 volt as the biasing voltage because it is 0. 1.4 it is starting, but you can see that it is not exactly following, right? 1.2 it is not still parallel. 2, 3, 3.54. I can now have the biasing voltage with respect to the DC biasing of the M1. Okay, somewhere after 4 I can say that they are approximately going in terms of parallel. Exactly not, okay, but this is better than this now. Okay, the moment you try to get that. Okay, so that's why we ensure that V in is somewhere around 4 volt, the biasing voltage, that is the V, the DC bias. This is all about the DC bias I'm saying. Okay, so we could know the biasing of the M2 should be less than V out, and we have taken as 0.8 or 0.9, and the biasing of M1, which is V in, I'm now considering as 4 volts. Even you can take 3.5 volts and see. Okay, so better the biasing voltage, better will be the output in terms of the input. Okay, so this is about the DC analysis. Hope this is fine. Hope this is fine, the DC analysis. Yes, no. Now moving ahead from the DC, okay, so we'll go to the transient analysis. Okay, we keep the VDD, VSS, VB as it is. Only thing is we are going to change from V in DC to sine. Okay, because it's an amplification, it's all about sine, right? Sine, and the first parameter in this parenthesis is the DC biasing. Okay, that's what 4, and then this sine amplitude I'll take it as something like 1, and it is of 1 kilo frequency. Okay, then I have 0, 0, 0, and then I'll go with the 50 samples. Okay, then I'll try to do the transient analysis dot tran 0 to 5 milli, or I can go with something like 3 cycles I'll go with. Okay, so this is what my transient analysis is all about, and then I'll try to do this simulation. Yeah, again this visible trace, V in, V out. Yes, if you want, you can have one more add plot. You can take your V in somewhere over here. Yes. Now you can find out your things. Okay. So V in, this is 3, the y-axis. Okay, the bottom one. And if I just want to take this, it is 5. So peak to peak is 2 volts. Okay, so peak to peak input. Okay, peak to peak input. Just go here. Peak to peak input voltage is 2 volts now. Yes, I have to find what is the peak to peak of output now. Yes. So this, if I just go with my y-axis, vertical 3.121. Okay, and if I just go with the bottom one, exactly, it is 1.481. Okay, 1.481. 1.481 is the minimum peak, and what was the maximum I could get? This is 3.13. 3.13. Okay, if I just subtract, if I just subtract 3.13 minus 1.48, I get somewhere around 1.65. Yes, 65. 0.65 divided by, so 0.825. So gain. So I can get a gain which is nothing but what, 1.67 divided by 2, which is approximately 0.825. Okay, this is what we have. Yes. So you can see that input is 2 volts peak to peak. I'm getting the output to be somewhere around 1.65 with a gain of this. Just a minute, I just. Yeah, so hope this is fine. So input is 2 volt peak to peak, but output I am getting somewhere around 1.67. Okay, so approximately it is 0.85 times. So V out. Okay, so V out, or here V out is approximately 0.85 times the V in. Yes, this is what I'm having. That's what. But exactly it cannot be following, but 90% of the V in is what we are getting, and if we can still manage all the parameters, we can go up to 0.95 something. Okay, but very important thing is, what is the biasing of the V in is very important. Okay, so in this case, if I go in, this is the V in. Okay, so on this biasing voltage, okay, again I'll just show you on this DC, which is 4 volts. Okay, I'm trying to apply the the sinusoidal input with the 1 volt, minus 1 volt. Peak to peak is something 2 volts, and 4 volts is the DC biasing, and the sine wave, whatever we are giving in terms of 1 kilohertz frequency sine wave with a peak to peak of 2 volts is the input voltage for which I will be getting the output with respect to almost gain 1, not exactly but almost. Yes. Hope this is fine. What is the transient analysis? Okay, so if I just may ensure this is kind of a source follower, or in other words, whatever the input is there, that's what I'll get at the output. Okay, it won't do the amplification. Okay, it is a kind of follower. Input output is follower of the input. Yes. Yes. Any clarifications here? The DC and the AC analysis. Sorry, the transient analysis. First. Yes. Any clarification in this common drain amplifier, which is basically a source follower? Okay, with the gain of approximately 1, but practically between 0.8 to 0.95 times. Yes. Similarly, we can go ahead. See, I mean, all these analysis are important now. What is this basically? Okay, so how to choose a DC operating point? Okay, so suppose if I try to change this DC operating point, okay, so from 4 to somewhere 3.5, we'll see whether something helps or not. Okay, this is save. Okay, tools, Spice, right click. Yes, I'll try to see what really happens with the gain there. Visible trace, V in, V out. Okay, and plot. We'll take this V in somewhere here. See, the moment biasing reduces, you can see that. So this also changes, right? So input peak to peak is changing now because biasing is reduce the biasing voltage, and correspondingly you can check what is. So input peak to peak is somewhere around 4.5 is the 4.5, and this is 2.5. I think still it is 2. I mean, yeah. So it is 2, and if you want to try with this, yeah, this is 2.7, 1.08. So it is 1.7 somewhere. Yeah, but 2. So it is 1.7 divided by 2. Again, approximately somewhere there I am getting. What if I try to change this to somewhere around 4.5, and we'll try to see. Okay, can just yeah, try to add a plot. Take this in there, and any of the input, and we are interested in the output here. .56, 1.88, 3.56, 3.56 minus 1.88 is 1.68 divided by 2. It's approximately 0.84. Okay, so that's what. Okay, so make sure that you try to see between 3.5 to 4.5 something, and you choose approximately which is the best biasing. Okay, so if you get somewhere a 0.87 compared to 0.5, I think 0.87 is the better one. Okay, so you can see that output is just following the input. Okay, so can you see any phase shift here? Can you see any phase shift similar to your common source amplifier? First.
No, sir.
No. So, okay. So this is just a follow. That's what we say. It is a source follower. Okay. So make sure your common source amplifier is a inverted. Okay. That phase shift minus is because of that shift where the output is amplified with respect to input, whereas here it is not. Now, can anyone tell me where exactly we try to use this now? Yeah. Where exactly we try to use this common drain amplifiers now? Yeah. Fast. Yes. Where's the application lies? Hmm. And what is the characteristics of common drain amplifier? Yes. So the characteristics, important characteristics is it is having high input impedance, and it is having low output impedance. This is the feature of common drain amplifier, high input impedance and low output impedance. Can now using this as an int, can anyone tell me where exactly we make use of or we use this common drain amplifier? Yes.
Impedance matching.
In what matching?
Impedance matching circuit.
Impedance matching, exactly. So the one of the application of this common drain amplifier is in the impedance matching. In the impedance matching. So this is what is very important for us, right? So what exactly we mean by impedance matching now? Okay, for example, assume that there is a one circuit, maybe it is an amplifier, I don't know. Yeah, this is an amplifier, okay, whose output impedance is high. Okay, I have one of the amplifier here, one of the circuit which I call it as amplifier, whose output impedance is high, and I have one more circuit at the other end, which is another amplifier, which has low input impedance. Yes, this is having high output impedance, and the second one is having the low input impedance. Now, I want the output of this to be connected to the input of this. Will it hold good? Can I do that?
No, sir.
No. What is the problem if I try to map high output impedance of one with the low input impedance of others? What will happen now?
Loading effect.
Loading effect. What is the inference of that? What do you mean by loading effect? There will be a signal loss, right? If the impedance is not matching, there is a signal loss. Yes or no?
Yes, sir.
Yes. So now what I'll try to do is, in between this, I'll try to introduce just now what we designed, that is the CD amplifier. Okay. Now can I connect the output of the amplifier 1 to the input of the common drain amplifier? Yes or no? Yes or no? Yes. Why? Because the amplifier 1 is an output having high output impedance. The common drain input impedance, okay, input impedance is high, whose output impedance is low. That's why we are now trying to connect this with this now. So high output impedance of amplifier 1 is connected to the common drain amplifier whose input is also high. I mean, it is having high input impedance. So there is a match. Similarly, there is a match with respect to the output of common drain amplifier and the next stage amplifier input, which is because both are of low impedance. Yes. So this is what coupling. Okay. So common drain amplifier can be used as a coupling device in order to match the impedance. Yes or no? Is there any loss now? No. Suppose if this amplifier peak to peak is 2 volts, here I'll be getting somewhere around 1.7 or 1.8. Not an issue for me. Yes or no? Yes. Okay, so your common drain amplifier is used for impedance matching between any two circuits. Okay, and an example is if one of the circuit wants to, if one of the circuit whose output I output, which has I output impedance, wants to connect to the another circuit which has low input impedance, then there is a mismatch, there is a loss of signal. Okay, so in order not to happen this, I'll try to introduce a coupling device. In this case, it is a CD amplifier. Okay, which will just exactly match the impedance now. Along with that, there will be very less signal loss from one circuit to the another circuit. Hope this is fine. The application of common drain amplifier. Yes. So your common source amplifier is for amplification. Okay. So for common drain, which is basically a source follower, where output follows the input, just it. That's it. V out follows V in with the gain of approximately 0.9 times. Not exact, like never I can get one. Okay. Practically, if I'm designing the common drain amplifier in the purest manner, I may go beyond some 0.95 or something like that. Up to, not beyond that. Yes. And the characteristics of this is it is having high input impedance and low output impedance, and because of that it is used as a coupling device sometimes. Okay, which couples one stage with another in order to match the impedance and also to reduce the signal loss. Yes, any doubts in this common drain amplifier design? Yes, I'll just,
Sir, hello.
yeah, yes.
Sir, since you mentioned those characteristics, sir, can I say it is also kind of a stabilizer kind of a thing, like in application wise?
It is not a stabilizer. What do you mean by stabilizer? I am not freezing anything, right? My input changes, my output changes. That's it.
Like, sir, like high input to low input. So I kind of thought like that.
It's not. It's not. It's not. It's not. Stabilizer is not kind of thing.
Okay, sir.
It is basically matching the impedance. That's it. If there is some mismatch, it is matching.
Okay, sir. Got it.
Yeah. So just a recap of thing. Okay, for the common drain amplifier. Okay, so this is the simple circuit here, where M1 is the driving circuit driven by the input voltage. Whenever you are, see, make sure whenever you are doing the AC analysis, the DC voltage is a mandatory, the biasing. Is that clear? This has to be biased. This has to be in the on state in order for the AC analysis. So that's why that AC on top of DC. Okay. So this is one, and this is the source resistance. And this source resistance is replaced by another MOS transistor. And this has to be again biased in order for this to operate in the saturation. Both the transistors should be operated in saturation, for which I am saying VDS1 minimum should be VGS1 minus VTH, or even beyond that is okay for me. Yeah. And gain is typically given by this, approximately theoretically it is 1, but practically in terms of 0.8 to 0.9 times. Then we have to find out what is the W by L of M1 and what is the W by L of M2, starting with the current equation in the saturation region. Okay, and that is what we did. In the first, we started with the M1 transistor analysis with the drain to source current, through which we try to get what is the V out. Okay, considering the VDD, VTH, the W by L of NMOS, and assuming IDS to be some current, and mu-n and COX we can get from the model library. Okay, that is C5 underscore models for NMOS. And substituting all this, we could get the V out to be somewhere around 1.4 volts. Then with the second M2 current equations, okay, we could get what is the W by L of second NMOS transistor, that is the load, which is acting as a load here, where VDS is replaced by V out, because drain to source is nothing but the V out of the W, the M2. And we know the V out, we know COX, mu-n and IDS2. and we can calculate what is W by L after substituting all those. We got somewhere around 4.59, which is approximately 5 I am taking. And here W by L we know, I'm just assuming L to be 4, whereas width is 20, and I'm getting, and L is 4 means width I could get 20. So W by L of NMOS is known, W by L of PMOS is known. I just went with the schematic of this thing, and then I could define the VDD and VSS and the biasing voltage for the load M2 in order for the saturation. Make sure your VB is less than what is your V out. Okay, that ensures that your VDS is greater than the difference of VG and VD. That's it. Okay, because of for the saturation. And then when you do the DC analysis, varying your V in from 0 to 5, the steps of 0.01. So there we have to, from the DC analysis, we have to find out what is the biasing voltage for M1. Okay, and you have to choose accordingly. That is when exactly the V out follows V in terms of parallel. Okay, and you see from which voltage onwards V out and V in are parallel. Okay, so that's what. And once you get that, you can do your transient analysis, and in the similar way you can finally do the frequency analysis, okay, with AC. Okay, so for AC, what exactly we try to give in terms of decade, 100 steps of 100, and then 100 G. This is what, right? Anything else, or it's okay? Is it what you have to specify for the AC analysis? Fast. Yes, no. Leave it. Spice height. Yes. Yes. And then just visible trace and just put V out. Okay. You can see that what exactly, and from this you can find out what is your thing. Okay, so this is about your AC analysis. This is about your transient analysis. This is about your DC analysis in order to find out the operating biasing voltage for M1. Biasing voltage for M2, you'll just ensure that it is less than the V out. Yeah, and now this is all about your common drain amplifier design, followed by the simulation. And any clarification or any doubts, I'm happy to hear from you. Otherwise, you can just call it a day. Make sure that you practice. See, try to change this biasing voltage of the M2 also from 0.9. You can keep it some 0.1 volt or something like that, and you can see how much I have kept here. I have kept somewhere around 0.8. Okay, so I can just keep some 1 volt, and I'll see what really happens. And here I will try to do some DC analysis first. Yeah, 0. 0. V in 0. DC 5. So dot DC V in 0 to 5 steps of 0.01. Let's see what really happens now. Save yes. Visible trace. You can just go with V in, V out. Say okay. You can almost getting same from before. Yeah, not much change from 0.8 to 1 and all. Okay. Yeah. So any clarification? I'm happy. Otherwise, I think we can leave here. Yeah. If no more doubts, thank you.